Hi, good day. My name is Shabir Madhi, and thanks to Sama for inviting me to give you a talk on COVID-19 vaccines, and particularly in the context of where we stand in South Africa. So I'm sure that by now, most of you have heard an enormous amount around COVID-19 vaccines. So just bear with me if you've heard some of the initial part of this talk, but just to put into context where we are, I thought it would be useful briefly just to reflect on what the development has been around COVID-19 vaccines, which has been a spectacular scientific achievement, being able to achieve what we have in the space of less than 12 months, when it would usually take almost 10 years to be able to develop a vaccine. And then I'm going to touch on the whole issue of what we've learned over the past 18 months or so when it comes to COVID-19 immunity, both following past infection, as through natural infection, as well as that which is induced by vaccines. And then drill into what our current understanding is when it comes to COVID-19 vaccine effectiveness. And obviously of particular interest to us, if not globally, is how well these vaccines work against the variant, which is very much dominating world news, and that's the Delta variant, which is at least 2 times more transmissible than the original virus that was circulating. To the last part of the talk, what I'll briefly touch on are some of the additional considerations around COVID-19 vaccines. In particular, one of the frequent questions that I'm asked is regarding how long should people wait? When is the best time to be vaccinated after an individual has been infected? Important to healthcare workers is, many of whom receive the Johnson & Johnson vaccine, is should I get the booster dose of vaccine? And if so, which booster dose? And in that context, I'll speak a little around heterologous COVID-19 vaccines and at least the immune responses that we've come to appreciate that sort of an approach doesn't use. And then last but not least, to discuss briefly what is my thoughts on herd immunity, which I believe is very much now becoming the scientific mainstream in terms of where we're heading to with COVID-19 as a pandemic and future control. So as I mentioned, usually it takes close to 10 years for vaccines to be developed, from the time when the vaccine is conceptualized in the lab to the time when the vaccine is eventually authorized for use and approved by regulatory authorities. What we've seen with COVID-19 is that this average of 10.5-year time frame has been condensed into a 10.5 months time frame. But I need to emphasize that has not come at the cost of adequate evaluation of the safety of the vaccine or the efficacy of the vaccine. And I'll touch on how we managed to condense what really should have taken 10.5 years into a 10.5 months period. Had we not done that, essentially what it would have meant is that a large percentage of South Africans and others would probably have developed, would probably have been infected with the virus by the time if we had adhered to a 10-year timeline, and the virus would have taken a much greater toll than it has already taken, not just in South Africa, but globally. Now, previously, the vaccine that probably took the shortest duration of time to develop was a mumps vaccine, which is a live attenuated vaccine. That took about 4 years. But if that same vaccine was to be evaluated in the current day and age, with the current regulatory requirements, that too probably would take close on to 10 years. So how did we manage to achieve what we managed to achieve? Like I said, development of COVID-19 vaccines has been a phenomenal success. Very few people, round about even this time last year, a year ago, would have predicted that not would we have just 1 or 2 vaccines, that we would have 19 COVID-19 vaccines at this point in time already authorized for use by one or another company, in addition to which there are 33 other COVID-19 vaccines that are currently in clinical trials, which many of which hopefully will also be authorized for use in a space of the next few months. But at the same time, there have been some failures. Up to 5 vaccines have not actually moved on into being used in populations because those vaccines, for various reasons, either were found not to be adequately immunogenic, the protection that they was inducing was far inferior to compared with the other vaccines that had already been authorized for use, etc. So we're in a really good space. Now, I'm not going to go to the detail of each of these vaccines, except to say for many of these vaccines, they've been authorized both in Northern Hemisphere, Southern Hemisphere countries, on the East as well as Western Hemisphere countries. But there are some vaccines that are more used in high-income countries, especially in North America, especially in Europe. And those include vaccines such as the Pfizer vaccine, the Moderna vaccine, the Johnson & Johnson vaccine, and the AstraZeneca vaccine. In many other parts of the world, there are other vaccines that have been used, including the Sinopharm vaccine, the Sinovac vaccine, and these are just names to you right now. And I hope that you do understand some differences between these vaccines, which I will touch on briefly. But bottom line, many of these vaccines have been authorized for use. For almost all of the vaccines that have been authorized for use, these vaccines have been shown to be remarkably successful, having high levels of protection, especially against severe disease and death. When it comes to protecting against mild infection, these vaccines do differ in their efficacy, something that I'll speak to about as well shortly. So why is it we've been able to achieve what we have with a 10.5-month period as opposed to a 10.5-year period? Now, as a brief introduction, when developing vaccines, as well as any other biological, there's different stages that you go through in that clinical evaluation process and a development process. What I'm not going to speak to about here is a preclinical development. And the preclinical development really refers to that which is happening in the laboratory, as well as that which is occurring in animal model challenge studies, or in animals, and included amongst those animals are mice as well as non-human primates. Now, what do we try to achieve during the preclinical stage is firstly, we're wanting to make sure that these vaccines are not inducing such a reaction that essentially kills off the animals. So we need to have some level of certainty with regard to the safety of these vaccines, at least in animals. In addition to which, at that time point, we also use that as an opportunity to get an early readout as to whether the vaccines are doing what we expect them to do. As an example, if we are giving a vaccine, we expect it to mount antibody responses. We would like to see those sort of antibody responses in these animal model studies. Now, these animal model studies, it's not any type of animal that would be suited for different vaccines. There are specific models that are developed and customized specifically to evaluate a specific product, be it a biological, or be it a vaccine. So when did this activity for preclinical models, for animal models, when did that activity to identify suitable animal models start? That activity, in fact, didn't start when COVID-19 was declared a pandemic. That activity has been ongoing. And I think what very few people realize is that the reason we've been able to get so quickly from the laboratory into humans is not because these vaccines have been designed and developed and the technology has been developed overnight. When you look at vaccines such as the AstraZeneca vaccine, as well as the Johnson & Johnson vaccine, your non-replicating vector-based vaccines, those vaccines, the use of that technology has been in the pipeline for decades, for more than a decade. In fact, for AstraZeneca vaccine, as an example, the scientists that were probably way ahead of the field when they announced that they've now got a vaccine that probably could protect against COVID-19, a few months after the pandemic was declared. The reason for that is that those very scientists had been using the same technology, the same platform to develop vaccines against SARS-CoV-1 and MERS. Now, they went to a reasonably advanced stage. They didn't get beyond phase 1 human studies, but all of that work to develop vaccines using that technology against coronaviruses was already in place. And all they needed to do, because of the type of technology that they were using, it was very amenable to being adapted, and consequently, they were rapidly able to change the target from MERS or SARS-CoV-1 to SARS-CoV-2. Messenger RNA vaccines, many of us are under the impression that this is a completely new technology, it never been used in humans before. But unfortunately, that's not true. The entire agenda of messenger RNA technology as a means for not necessarily a vaccine, but as a therapeutic option, has also been in the pipeline for more than a decade. Again, a type of technology that is very amenable to being changed, to being adapted for a different purpose. Historically, the technology has been more geared towards trying to develop customized therapeutics in individuals with cancer. It can be specific, what we call precision medicine, where we're now really customizing interventions to the individual. That is the type of technology that could be and is already becoming game changers in the field of cancer therapeutics. So important to emphasize the reason why this preclinical development didn't take what would average be close on to 3 to 8 years is because, in fact, much of it has been taking place over the past 3 to 8 years, but not for SARS-CoV-2, but in the context of other vaccines. So then we go into clinical phases. Now, what are clinical phases? So before we go into the clinical phase, what we're also doing in this preclinical development is we ensure that these vaccines are actually working and at least able to probably protect against the disease. So we do what we call animal challenge studies, where we vaccinate the non-human primates or vaccinate the mice, and then inject them into the nose or even in the lung with the virus, as an example. And then we follow them up for clinical well-being. We obviously, under all of the circumstances, you've got two groups. You've got the mice that are receiving the intervention, those mice that are not receiving the intervention. You do exactly the same procedures, do the same sort of follow-up, and then we see the difference. And we find that mice that were vaccinated before being challenged tend to survive longer, have better activity, have less pathology when they sacrifice, when looking at the lungs, than the mice that weren't vaccinated. So that is an important piece of the puzzle. And it's only after that has been completed that we go into phase 1, phase 2, and phase 3. Now, in general, companies that are developing these vaccines are expected to take on the risk of the clinical development of the vaccine, including the financial risk. So companies generally are averse and they risk averse, and they wanting to ensure that there's a high likelihood of success before they go to the next step. Because by the time they come into the phase 3 trial, it is going to cost anything between $500 million and $1 billion for them to eventually complete that phase 3 trial, depending on the size of the trial. So what companies do is that they're very cautious in terms of making the decision-making with regard to going from one step to another, because they can't put a huge investment on a product which might have a very low likelihood of success. Now, that entire funding model for development of vaccines was changed when it came to COVID-19. The financial risk component of this was largely removed from companies, and that sort of responsibility was taken over by governments, including the government of the United States, as an example, that put in more than $2 billion, gave it as a promise to companies that you come up with a successful product or you go through your phase 3 trial, we are willing to basically pay you upfront now for the equivalent of maybe 100 million doses after the vaccine has been shown to work. And should that not have been shown to work, the United States government was willing to basically take the financial knock from that, something companies wouldn't be able to do. So with that sort of a paradigm, what usually happens with phase 1, phase 2, phase 3, and phase 1 is when we usually evaluate small numbers of individuals just to look at what might be serious immediate side effects, as well as to look at the immune responses to different dosing schedules. Phase 2 is a larger study where we look at different dosing schedules, or we rather select which dosing schedule we're wanting to now use, look at it in a larger population of individuals. It also allows us to now explore further the safety profile in a larger number of people, which means that side effects that are relatively less frequent can now be picked up in a phase 2 study where you've got perhaps 1,000 to 2,000 people enrolled. But at the same time, in phase 2, at times, we can also get an indication as to whether the vaccine is going to work or not. When we go to phase 3, and this is studies now that involve between 30,000 and 40,000, and at times even 60,000, depending on a number of factors, how you determine your sample size. And this is when there's a randomization in all of these human trials, phase 1, phase 2 to 3. There's what we call a double-blind randomized control. And that's important because it avoids any sort of biases creeping in, where neither the investigator nor the participant know which arm they've been actually allocated to. They receive the study medication or study injection without, again, knowing what it is they're receiving. They're systematically followed up. And at the end of the day, any differences between those two groups, and those two groups will generally be balanced when it comes to their demographic features, when it comes to their risk factors, whatever it is, because it's a random assignment, which is sometimes mostly computer generated now as to which group one person or another would go, which is completely agnostic to that person as an individual. That randomization eventually gets us to a position where if there are any differences between these two groups, those differences, whether good or bad, can be attributed to the vaccine. Because one group as a control usually receiving, as an example, a saline, and the other group received the vaccine. And any difference between the two is basically a consequence of the vaccine. And that allows us not to evaluate just the efficacy of the vaccine, but also the safety. Because if we find one medical condition is more common in a group that received the vaccine, that means the vaccine very likely caused that condition. And that's the reason for the difference between the two groups. Now, I'm not going to bore you about immune responses to SARS-CoV-2, but just as a quick background, I think, and this is something that's familiar to all of you, the purpose behind vaccines is to try to do pretty much what natural infection will do, but to do it in a much more refined manner and result in a much more predictable outcome than would usually occur with natural infection. And in addition to which, when we're using vaccines, generally, which are much more targeted with regard to which component of the virus we're wanting to include in the vaccine. There are some vaccines that uses the full virus itself. So as an example, polio virus, where we've got live attenuated vaccines as well as inactivated vaccines. This is using the entire virus. It's being sort of manipulated to such an extent that it wouldn't cause severe disease in a child, as an example. It won't cause the classical polio signs and symptoms, but at the same time, it would allow for the elucidation of an immune response. So when it comes to COVID-19 vaccines, what we really understand of this virus is that there's this protein on the surface known as a spike protein. And that is an important component of the virus in that the virus uses the spike protein to adhere to what is known as the ACE2 receptors on the human cells. That engagement of the spike protein and ACE2 receptors allows the virus to gain entry into the cell, and then we start having all of the problems that we experience with COVID-19. The problems of COVID-19 is a consequence of largely the immune response to the virus, rather than the virus just going rampant and destroying tissue, as an example. So as part of this process, what usually happens is that at the initial phase, the body, especially if a person is immunocompetent, that virus is sort of contained within cells, but at the same time released into the circulation and then taken up by what is known as antigen-presenting cells. Now, those antigen-presenting cells then again process the virus and start sort of expressing on its surface or to other cells components of the virus. And the ones that we are especially important on, as I mentioned, is the spike protein. But in addition to the spike protein, when the whole virus is given, there's a number of other proteins that are also presented by the antigen-presenting cells to the other immune cells in the environment. Now, the immune cells that are of most interest to us from a basic perspective are what we know as the T helper cells. These T helper cells are especially important in terms of allowing for the differentiation and the proliferation of other categories of immune cells. And the two important ones for our purposes are the B lymphocytes and the CD8 cells, which are otherwise also referred to as the cytotoxic T cells. So these B lymphocytes, as we all know, are very important when it comes to adaptive immunity, especially inducing humoral immunity, production of antibody. The antibody that's now produced is dependent on what was eventually presented to those B cells, which allows it to differentiate and start producing antibody specifically against the target that was presented to it via the antigen-presenting cell. For most of the COVID-19 vaccines, the antigen that we're using is really the spike protein. There are new generations of vaccine that might use other components of the virus, including the nuclear protein, the N protein. And then there's another category where the entire virus is being used, which I'll come to briefly. Now, why is all of this important? So what's happening now is we've got differentiation, and we've got proliferation of B cells and the T cells. The B cells produce the antibodies. These antibodies play two important roles. The first is that they now recognize that spike protein, and antibody attaches to the spike protein. What does that assist? It prevents that particular virus from now adhering to the human cell. So this can actually prevent infection. But sometimes the antibody doesn't actually adhere to that spike protein adequately, especially if there's mutations of the spike protein. That antibody is going to become less able to be able to adhere to that spike protein, and consequently you end up getting breakthrough infections, as an example. The other purpose of this antibody is that when it adheres to the spike protein, it also plays a role in terms of the eventual destruction of the virus. Now, our understanding, as I'll show you, is that these antibodies play an especially important role in protecting against infection and preventing mild disease. The other arm of the immune system that's also induced is your CD8 cells, and these are your cytotoxic T lymphocytes. Now, these play an especially important role in controlling the application of the virus and destroying the infected cells so that the virus can't continue replicating in those cells and can't continue sort of infecting other cells in the human. So if we've got this cytotoxic T lymphocytes available to us, as soon as a person is infected, we expect those viruses, those cells to start acting, destroy those infected cells, preventing the virus from being able to replicate. Remember, a virus is not a living organism. The success of a virus to replicate is completely dependent on the host machinery. If you remove the cell from which the virus is actually sort of harboring itself in, the virus can't do anything else. It can't replicate. So two arms of the immune system, antibody production that's through the B lymphocytes and then your cytotoxic T lymphocytes. And most of the evidence suggests that the cytotoxic T lymphocytes are especially important in protecting against severe disease. So it's possible and highly likely what we're seeing currently is that breakthrough infections are occurring due to the Delta variant because the Delta variant is slightly less susceptible to this antibody activity of vaccines that were really designed around an ancestral virus that had a slightly different spike protein without the mutations that are currently being identified in the spike protein of the Delta variant. So the antibody functionality against that virus is slightly attenuated, hence we get more breakthrough infections compared to what we had observed for the ancestral virus, in addition to which there might be some issue around waning of immunity. But when it comes to protection of severe disease, despite the mutations that have already occurred in the spike protein, be the beta variant, the one variant that started off in South Africa or first identified in South Africa, be the Delta variant or the Gamma variant. These vaccines, including the AstraZeneca vaccine, which didn't protect against mild infection due to the beta variant, as I'll show you, have worked extremely well and have got sustained protection against severe disease. And the only way to explain that is either you require very little neutralizing antibody to protect against severe disease, or it's because of the major role that these cytotoxic T lymphocytes are playing in that sphere. So like I said, there are four different sort of types of COVID-19 vaccine. And I'm briefly going to touch on each of these. The mechanism of it is almost identical. At the end of the day, you're trying to present, as I mentioned, a specific peptide. For three of the four technologies, it's specific the spike protein that you're trying to present to the immune system to induce the B and T lymphocyte responses. Now, the category of vaccines that differ to the other three is really the attenuated and inactivated vaccines. In this instance, you're taking the actual virus, you're inactivating it, or you creating mutations to such an extent that the virus, although inducing an immune response, won't necessarily be able to actually cause disease. There aren't any live-attenuated vaccines that are currently licensed. So let's look at inactivated vaccines. The difference between these inactivated vaccines is that a whole lot of peptides, different components of the virus that are being processed by the host immune cell. So the repertoire of immune response that is being induced is very, very different compared to the repertoire of immune responses that's induced by a vaccine that's using a small section of the virus, specifically the spike protein as an example. So you've got the different repertoire of immune responses. Generally, the amount of what we call neutralizing antibody, the antibody that's induced by the vaccine that's able to sort of in vitro neutralize the activity of the virus, sort of prevent the virus from infecting cells in vitro, the neutralizing antibody concentration of the live inactivated vaccines is lower than what we observe for the other vaccines. And I'll show you that data as well. So what are examples of these two vaccines? The ones that everyone has heard about in South Africa, probably Sinovac, inactivated vaccine. And there are already three vaccines that have already gone, inactivated vaccines that have gone through phase 3 trials, and all of three of them are actually being used. In fact, I think maybe 4 of the inactivated vaccines make up those 19 vaccines that are currently being used under emergency use authorization. Then we've got a more traditional approach of the vaccines, and that is virus-like particles or protein subunit vaccines. The virus-like particles, an example of that type of a vaccine is HPV vaccine, human papilloma virus. Now, for the protein subunit vaccines, this is a more traditional approach of developing vaccines, although the type of technology that's being used differs. And the vaccine that's furthest in clinical development with the subunit-based vaccines is the Novavax vaccine. In South Africa, we evaluated the Novavax vaccine as well. It's a subunit vaccine, as I mentioned, and as I'll show you, it's amongst the top 3 vaccines when it comes to the magnitude of antibody response that's actually induced, as well as when it comes to its efficacy, including its efficacy against mild to moderate COVID-19. So Novavax is currently being considered by a few regulatory authorities for approval, or at least for emergency use authorization. But other than the Novavax one, there aren't any other vaccines that have completed phase 3 trials that have used a subunit approach. Now, the 2 other sort of technologies is your gene-based vaccines. And although the RNA and DNA vaccines are seen as being different from the non-replicating vector-based vaccines, the major difference between these 2 vaccines is a mechanism in which the genetic material is actually being presented to the host cell and eventually presented onward to the antigen-presenting cell and inducing an immune response. With the messenger RNA, these particles are being sort of, in a sense, encapsulated in a lipid type of particle, injected into the muscle. Once in a muscle is released, that liposome is sort of degraded, the messenger RNA then becomes available to the cell. It uses the cell's machinery essentially to read the code that's been presented to it and use that to actually produce a protein, which is what our cells always do. Our cells are always there to be producing things, including proteins, for our own bodies. So importantly with these gene-based vaccines is, like I mentioned, just perhaps to wrap up first on that part of it. So both of the different with the non-replicating vector-based vaccines, there aren't any replicating vector-based vaccines currently in use. AstraZeneca, Johnson & Johnson as an example, Sputnik 5, those are non-replicating vector-based vaccines. What you're doing now is that rather than encapsulating the genetic material into a lipid particle or liposome to basically inject into the muscle, we're now inserting that genetic material into this virus, which doesn't cause illness in humans. And it hasn't got the ability to actually replicate. We insert the genetic material in, inject it into the muscle. Once in a muscle, that genetic material is again released, and then it makes use of the host machinery to produce these proteins, the spike protein in this instance, which are then presented to the immune cells to induce the T lymphocyte responses, including the cytotoxic T lymphocyte responses and the B lymphocyte responses. And what I forgot to mention is that these responses that are induced then sort of after a while go into what we call a memory phase. The difference being that those memory cells are much more quickly recruitable and they become much more quickly active when a person is re-exposed to infection, so that it doesn't take 2 to 3 weeks before our immune system, our adaptive immune system, is able to kick in to try to control the infection and the spread of the virus, which is what vaccines are all about. So what are RNA vaccines? The ones that we're all familiar with are the Moderna vaccine and the Pfizer vaccine. There's a couple of few more RNA vaccines, now also known as self-replicating RNA vaccines, rather than just messenger RNA vaccines that are currently in clinical trials. Another important issue of this gene-based vaccines is that not included in this presentation is the ability of the virus or that RNA to actually integrate into the human cell. So these RNAs actually degraded fairly rapidly after that code is read by the ribosomes and the protein is actually produced. After that has taken place, these the RNA material, the genetic material from these vaccines are degraded very quickly. They do not integrate. They don't have the ability. They're not living to start off with, but they don't have the ability to actually integrate into the human cell. They cannot make up part of our DNA moving forward. End result of all of this is, again, aim is to produce antibodies, aim is to induce cytotoxic T lymphocytes, so that when we're exposed to the virus, we can react quickly to it, prevent the infection from taking place. If we can't prevent the infection to take place, at least get infection to abort as quickly as possible because of the activity of these immune cells. Now, as I mentioned, we've got 19 different vaccines that are currently authorized for use, but these vaccines do differ. They differ in terms of the magnitude of antibody response, and I'm going to be referring to neutralizing antibody. There's also what we refer to as binding antibody. They're sort of the same, but at the same time, slight differences between it. So let's just talk about antibody. But I would be sort of interchangeably could be referring to binding antibody or neutralizing antibody. Now, as I said, a neutralizing antibody is the antibody that's actually present that shows in vitro the ability to prevent the virus from infecting cells. And that neutralizing antibody seems to be an important measure in terms of what we can expect when it comes to how well COVID vaccines work in protecting at least against mild to moderate disease. So when we look at these different vaccines, we find that the first issue is that it's difficult to make head-to-head comparisons between these different sort of responses of the different vaccines because it's not the same assay that has been used, in addition to which they've been benchmarked against perhaps a different standard when measuring the immune responses. But that being said, all of these vaccines have been benchmarked in terms of the magnitude of immune response over and above what is actually observed in people that have recovered from COVID, what we know as convalescent sera. But there's a clear trend. What we find is that for many vaccines, for some vaccines, the messenger RNA vaccines and the Pfizer, both the BioNTech, Pfizer, as well as the Moderna vaccine, the magnitude of immune response, of the neutralizing antibody response that's induced relative to the convalescent sera is far greater than what we observe as an example for CoronaVac or Sinovac or Sinopharm, with your vector-based vaccines coming in between your messenger RNA vaccines and your Novavax vaccine. This is a Novavax vaccine. So the Novavax vaccine, a Moderna vaccine, Pfizer vaccine, these vaccines, the magnitude of the fold increase in neutralizing antibody responses above that of convalescent sera used in those particular studies is much greater than the fold increase above convalescent sera neutralizing antibody that you observe as an example for AstraZeneca, for Sputnik or J&J. So what we also see is that this sort of difference in magnitude of immune response does actually translate into a pattern with regard to what we see when it comes to the efficacy of the vaccine. So vaccines such as the messenger RNA vaccine and Novavax vaccine, and this is efficacy against the ancestry virus, those vaccines that induce higher antibody responses end up with higher efficacy in the region of 95%, above 90%. Including for Novavax against the ancestry virus or even and the alpha variant for that matter. Whereas those vaccines that induce more modest neutralizing antibody responses, such as the AstraZeneca vaccine, such as Johnson & Johnson vaccine, we're getting vaccine efficacy in a region of about 70%. But importantly to emphasize, this is efficacy against a full spectrum of disease, and most of the endpoint, most of the efficacy that's been measured here is efficacy against mild to moderate COVID-19. Not against severe disease. Severe disease makes up a fraction of all of the endpoint cases in all of the studies. So we're mainly measuring efficacy against mild to moderate COVID-19. These vaccines work especially against ancestry virus as well as against the alpha variant. And that is the time when most of these vaccine trials were done. And I'll come to subsequent experiences. With Sinovac as an example, there are differences in the reporting of efficacy. There's a study from South America which reports efficacy of Sinovac of, I think, roughly about 50%. In Turkey, that's about 80%. So there are differences between places as well. And there can be a number of reasons for that. So the most important message here is that all vaccines work extremely well, as I'll show you, in protecting against severe disease, with efficacy and effectiveness above 80%. But when it comes to being able to protect against mild disease, moderate disease, against infection, there's variability with regard to vaccines, and vaccines such as Pfizer certainly would work much, much better than against a single dose of Johnson & Johnson in protecting it against mild infection. And I think the type of breakthrough events that we've seen in healthcare workers is testimony to that we've seen lots of breakthrough infections, but very, very few, only 3% of the breakthrough infections with severe disease. And that tells us indirectly that these vaccines don't, especially J&J as an example, doesn't necessarily protect you that well against mild disease, but when it comes to protecting against severe disease. And that is the reason we have vaccines. We don't have vaccines. We've never in the history of mankind started to develop vaccines to prevent infection. The purpose and the main goal of vaccines is to protect against severe disease and to prevent death. So what did we, like I mentioned, although there was variability, and these are different studies at an early phase of, at the early stages when we're getting efficacy readouts, although there were differences in the efficacy of these vaccines against mild disease, moderate disease, ranging from anything 57% for Novavax for Johnson & Johnson in South Africa, also that was due to the beta variant partly. In other places, we had 94% efficacy, even against mild to moderate disease. But when we looked at protection against severe disease across all of these, including Sputnik 5, and even you could add Sinovac to this, the protection against hospitalization and death was nearing 100%. So these vaccines were variable when it comes to the efficacy against mild to moderate disease, which is mainly, like I said, probably related to the quantity of antibody responses and possibly also the quality of antibody responses that's been induced. But even when there's very low levels of neutralizing antibody that's been induced, these vaccines are still having high degree of protection against severe disease. And obviously in these studies, they usually exclude people with major comorbidities, immunocompromised individuals. So when rolling out the vaccine into the general population, we don't expect it to remain at 100% because now we're vaccinating people that might have a suboptimal immune response to the vaccine, and consequently, we expect that efficacy both for mild to moderate as well as severe disease to decrease. But what we're seeing consistently is effectiveness against hospitalization of deaths still being more than 90% once these vaccines are rolled out into public immunization programs. When it comes to effectiveness against mild disease, that's subject to a number of factors, including new variants of concern, such as the Beta variant, where we've shown where the AstraZeneca vaccine, unfortunately, simply doesn't confer any protection against mild to moderate COVID-19, but at the same time, as I'll show you, the poor decision on the part of the South African government and its decision to get rid of the vaccine rather than introducing it and making it available to those that would have wanted to be protected against severe disease, the vaccine works actually extremely well against severe disease, even due to the Beta variant. So talking of variants, so this is obviously something that came somewhat unexpected. And initially, when these vaccine efficacy results were being reported, there was a huge amount of excitement. We've achieved a miracle, being able to develop a vaccine in such a short period of time. The benchmark that was set by regulatory authorities is we will give you approval to use your vaccine if your vaccine efficacy is 50%. What we saw with messenger RNA vaccines is not 50% efficacy, 94% efficacy. So things seemed really rosy. And with 94% efficacy against mild infection and against infection and mild disease, you could probably get to herd immunity if there weren't major changes in the virus. If the virus remains stable, there weren't mutations that make the vaccine less sort of effective against it, and the virus didn't become more sort of transmissible, places such as the United Kingdom, Israel, and United States right now would have already reached herd immunity, where more than 2/3 of the population has been vaccinated. But that has not happened for good reason. And the reason for that, unfortunately, is something which we probably underestimated. Right at the start, we didn't necessarily expect this virus to mutate as quickly as it has. And when these mutations have taken place, there are two major issues that has happened, which results in a virus being termed as a variant of concern. Firstly, the virus has become much more transmissible. That is, it's easier to spread between people, especially in a fully susceptible community. As I mentioned, with the Delta variant, it's at least 2 times more transmissible than the ancestry virus. What that translates into, as a back of the envelope calculation, with the ancestry virus, we needed to get about 65%, 2/3 of the population develop immunity against infection for us to get to herd immunity. Now with the Delta variant, we need to get 85% of the population develop immunity, not against severe disease, against infection or mild disease, or at least them not actually being able to pass on the virus. 85% would develop that type of protection if we were wanting to get to herd immunity. Unfortunately, the bad news is that ain't going to happen, not with the current generation of vaccines, and in all likelihood, unfortunately, not during the course of our lifetime. So we need to rethink about COVID-19, how we respond to it, and where we're moving in the future. So there's a number of mutations that takes place. Like I said, I'm not going to go into the detail of those mutations, except to say some mutations assist the virus in becoming more adaptable to being able to infect the host. And then other mutations basically allows the virus to evade the antibody that is being induced, specifically the antibody responses that of vaccines as well as from past infection. The virus is now able to evade the ability of that antibody either to bind to the virus or neutralize the activity of the virus in infecting cells. Now, where you start off with your neutralizing antibody will have a major bearing in terms of the type of change that you expect when it comes to the efficacy because of a mutation arising. So if you start off with a vaccine as an example, which has got a really good high antibody response to start off with, the neutralizing antibody response, as I mentioned, your messenger RNA vaccines, your protein-based vaccine, even if it is a twofold sort of reduction in the susceptibility of the virus to the activity of that neutralizing antibody, what you'd expect is a drop in efficacy, but the magnitude of that drop in efficacy will be much less than for a vaccine where there's also, that starts off at a lower point, where there's a twofold reduction in the sensitivity of that variant to the activity of the neutralizing antibody that was induced against the ancestral virus. The decline, the change, the sort of gradient, the magnitude of change of the efficacy or effectiveness will be much greater. So depending where in the spectrum you start, with regard to the quantity of antibodies, seems to be able to influence the type of effect a new variant of concern, which is relatively immunoresistant to the neutralizing antibody activity of the virus, what that effect would be in terms of fallout of efficacy. So hopefully that makes some sense to you. For some variants, as an example, the beta variant and the B16172, which is a Delta variant, there you basically got more than a 5-fold reduction in terms of the sensitivity of that virus to the neutralizing antibody activity that was induced by these vaccines that were designed against the ancestral virus. So then you expect even a larger drop in terms of your efficacy. But again, this is a decline in effectiveness of these vaccines, not against severe disease. These neutralizing antibodies, these blocking antibodies, seems to be more strongly associated with in predicting protection against mild or moderate COVID and infection, rather than how well they would protect against severe disease. So which vaccines you use will determine the sort of the decline in effectiveness if there is a new variant of concern that actually arises, because if you start with higher antibody concentrations, you're better off in terms of being able to deal when exposed to a variant of concern which has got relative reduced susceptibility to the activity of that vaccine. So briefly to talk on vaccine effectiveness against variants of concern, and specifically the Delta variant. So in November of last year, all of us heard about the new variant that had arisen in South Africa, known as the B1.351 variant, otherwise now known as the Beta variant. And when the scientists tested the samples of people that had recovered from past infection due to the ancestral virus, and the antibody that was induced by that past infection, and they tested that antibody for its activity against the Beta variant, much to our horror, the mutations that had taken place resulted in the antibody that was induced because of infection by the ancestral virus having very little activity against the Beta variant. In fact, more than 85% of people showed that were recovered from past infection due to the ancestral virus. They had antibody. That antibody was still showing neutralizing activity against the original virus. But when looking at a Beta variant, there was pretty much 85% of people didn't have any antibody, neutralizing antibody activity against the Beta variant. So this came up as a problem because this sort of somewhat predicted what would come next with some vaccines at least, because what we would expect is that if you got this drop in terms of neutralizing antibody activity, these vaccines are not going to work too well, at least not when it comes to protecting against mild COVID-19. And that, unfortunately, is exactly what we reported in January of this year, which seems to be a lifetime ago to me, where we, unfortunately, in the study from South Africa, we showed that because in the study, fortuitously, what ended up happening is that we started enrolling at a time when the first wave was peaking, but all of the endpoint cases that occurred 2 weeks after the second dose largely accrued by the time the Beta variant had pretty much started to dominate in South Africa. And when we analyzed the data, unfortunately, we showed that a vaccine didn't protect against mild to moderate COVID-19 due to the Beta variant. And again, I emphasize, it was mild to moderate COVID-19, and it's a real pity that some people don't understand a difference between mild to moderate COVID-19 and severe disease, and that what you require to protect against severe disease does not necessarily equate to what is required to protect against mild to moderate COVID-19. Another important thing of the study is that the hypothesis that was being tested here was whether we're able to protect or provide at least 60% or have at least 60% or greater efficacy. It might well be that the efficacy of the vaccine was only set to 40% against the Beta variant. But this study wouldn't have been able to identify that. You see that our confidence intervals for Beta variant is from minus 79 to 55, meaning that the truth could be anywhere between those two parameters. But what we can say is that efficacy wasn't more than 60%, which was disappointing, obviously. And that led to South Africa, the government and its advisors making an ill-informed decision which went against the World Health Organization recommendation that even in a country such as South Africa, where the beta variant was dominating, that countries should still use the AstraZeneca vaccine because there was a high likelihood that that vaccine would still protect against severe disease. And in fact, before the vaccine was actually shipped out, this study came out from the NIH, the National Institute of Health in the US, where in an animal model, in Syrian mice, what they were able to show is that when these mice were vaccinated with the AstraZeneca vaccine and they were challenged for the alpha variant as well as the beta variant, looking at neutralizing antibody activity induced, not surprisingly, there was very little neutralizing antibody activity against the beta variant, but good neutralizing antibody activity against the alpha variant. When looking at these mice in terms of the lung itself, in the lung, after they're now challenged with the SARS-CoV-2, what we observe is that irrespective of whether the mice were challenged with the beta variant or the alpha variant, those mice that received the AstraZeneca vaccine had little to no replication of live virus in the lung. And in fact, what they also showed is that looking at the lungs of these mice, gross anatomy as well as microscopically the histopathology, those mice that were vaccinated, when they were challenged either with the alpha variant or the beta variant, their lungs remained completely normal, completely clear. Those mice that were the control group were not protected, their lungs were completely damaged, irrespective of whether they were challenged with the alpha or beta variant, with severe microscopic disease. These data were already available to South Africa. To make a decision, to revise this decision, this poor decision to sell a vaccine, yet they decided to sell a vaccine with the evidence that the vaccine very likely could still work in protecting against severe disease. And the reason for that, as I mentioned, is unlike the neutralizing antibody, which seems to be severely affected depending on the mutations that have taken place in the virus, affecting the spike protein. When it comes to protecting against severe disease, it's about cytotoxic T lymphocyte responses, these CD8 responses. The type of mutations that have taken place in the spike protein has largely left the cytotoxic T lymphocyte responses that's induced by the vaccine completely unaffected, which means that these vaccines are still able to induce the cytotoxic T lymphocyte responses, which is important for the clearance of the virus eventually from the infected cells, as well as in protecting against severe disease. And this will hold true for the Delta variant as well, and the Gamma variant, and the Lambda variant. These are mutations that are largely at this point in time mainly affecting the spike protein. The cytotoxic T lymphocyte responses are basically also geared towards the spike protein, but they basically responding to different parts of the spike protein other than those parts which are more critical in terms of inducing neutralizing antibody responses. So we still got to divert this up to about the AstraZeneca vaccine as an example. The T cell responses is directed to about 87 different epitopes of that spike protein, 76 of which completely remain unaffected by the beta variant mutations, and all of the CD8 responses remain largely unaffected by the beta mutations of the spike protein. So vaccine effectiveness against the alpha, beta, gamma, etc. So this is a study from Canada, which is currently in preprint. And in this study where they basically were able to look at how well the vaccine works against the alpha variant, the beta and gamma were combined. Now the beta and gamma were combined because they were relatively of a lower magnitude in Canada, but these two variants of concern share a similar mutation, what is known as the E484K mutation, which reduces the antibody activity against these variants. And that's the reason why they've combined these two. And then you've got a Delta variant. So how well do these vaccines work against any symptomatic infection? This includes mild disease. After 7 days after second dose, let's first look at after 14 days after first dose. And this is for the messenger RNA vaccine, the Moderna vaccine, the BioNTech, the Pfizer vaccine on the left-hand side, and the AstraZeneca vaccine. 14 days after a single dose, even for the AstraZeneca vaccine effectiveness against symptomatic infection due to the alpha and delta variant is about in the region of 60%. Due to the beta gamma variant, that effectiveness is around about 50%. 14 days after a single dose of the vaccine. Our study wouldn't have been able to detect that because we were only powered to look at efficacy of 60% or greater. And as I mentioned, the efficacy could have been lower, but we might have still missed out whether it actually works or not. After a second dose of vaccine, this is data now for messenger RNA vaccines. Not surprisingly, you're going to have higher antibody concentrations, you're going to have higher magnitude of protection, and then your vaccine effectiveness across all different variants of concern, including beta, gamma for the Pfizer BioNTech vaccine. You got effectiveness in the region of 80%. For some, for Alpha, close on to 90%. For Delta, close on to 90%. When it comes to protecting against severe disease, it's even greater, both after the first as well as the second dose. In fact, after the second dose for the messenger RNA vaccines against Alpha as well as against Beta, Gamma, Delta, we got effectiveness in the region of 90% and above. For the AstraZeneca vaccine, including for against Beta and Gamma, and I'm going to harp on this just to emphasize poor decision-making, you got vaccine effectiveness of in the region of 80% against severe disease, hospitalization, and death with the AstraZeneca vaccine. For Delta, close on to 85%. Is that the only study that confirms that vaccine protects against the Beta variant? The answer, unfortunately, is not. With the Pfizer vaccine, these are data from Qatar, and I'm running out of time, so I'm going to try to just get through this very quickly. Clearly, after a single dose of the vaccine, because there's these mutations, the virus is less susceptible to the effects of the vaccine. What we find is that against the Beta variant, as well as against the Alpha variant, vaccine effectiveness 7 days after a single dose, and this is against all infection and disease, ranging between 30% to maybe 20%. After the second dose, effectiveness against the Alpha and Beta variant then goes up to 75% and up to 90% for the Beta and the Alpha variants respectively. When looking at severe disease, even after a single dose, we got already 50% protection with the Pfizer vaccine after a single dose and after 14 days after the second dose, and this is against the Alpha variant, close on to 90% protection, if close on to 100% protection. For Beta variant fatal severe disease with a AstraZeneca with a Pfizer vaccine, we got close on to 100. Sorry, these are not Pfizer vaccine. I think this might have been a combination. Sorry, these are the Pfizer vaccines, yes. Close on to 100% protection against severe disease after the second dose. Other data from the United Kingdom shows a very similar sort of scenario after a single dose with the AstraZeneca vaccine, as well as with the Pfizer vaccine, effectiveness against mild to moderate disease, slightly lower for the AstraZeneca vaccine compared to the Pfizer vaccine. For the Delta variant, for the Alpha variant, even after a single dose, you got already 50% protection after a second dose. For the second 14 days after the second dose, protection against all severity illness for the AstraZeneca vaccine sitting at about 70%, whilst it's 90% for the Pfizer vaccine. For Delta variant, that goes down to just under 70%, about 65%, and just around about 85% for the Pfizer vaccine. So this also shows us that vaccine efficacy, effectiveness rather, is higher against the Alpha variant compared to the Delta variant in the United Kingdom, and this is for all severity illness. But when we look at severe disease, very similar to what I described before, and this again data from Qatar, basically effectiveness against infection, basically modest. This is messenger, the Pfizer and the Moderna vaccines, in the region of 50 to 80%, but when looking at protection against severe disease, we've got 100%, close to 100% protection for both of these vaccines, and this is vaccine effectiveness against the Delta variant. So we can be comfortable that if you're fully vaccinated, including with 2 doses of AstraZeneca vaccine, your chances of ending up in hospital, even due to the Delta variant, is extremely low. Yes, you are going to have breakthrough infections. That is going to occur irrespective of whether you receive the Johnson & Johnson or the Pfizer vaccine, but you're probably more likely to have a breakthrough infection with the Johnson & Johnson vaccine than the Pfizer vaccine, because the Pfizer vaccine certainly produces much more higher antibody, neutralizing antibody responses, which hopefully I've convinced you is strongly associated in predicting the type of protection, not against severe disease, but against mild disease. So like I said, breakthrough infections take place. Can we predict or do we have an understanding as to who is more likely to have a breakthrough? And this is studies in healthcare workers. And the short answer is that amount of neutralizing antibody concentration at the time of the peak after the second dose of vaccine, as an example, is predictive as to whether you will have a breakthrough infection or not. So as an example, what you see is in peak neutralizing antibody responses, those individuals that have vaccinated individuals that had a breakthrough event, their neutralizing antibody concentrations were much lower than those individuals that didn't have a breakthrough event. And the same thing goes when looking at the peak IgG responses. So, and these are data mainly from with regard to the alpha variant, where 85% of these events occurred because of the alpha variant. And bottom line is that the type of neutralizing antibody concentration that you've got after vaccination will determine your risk of actually having a breakthrough event. Unfortunately, if you're going to get a single dose of Johnson & Johnson vaccine, the magnitude of the antibody response induced by a single dose of the Johnson & Johnson vaccine, and for that matter, even the AstraZeneca vaccine, 2 doses of the AstraZeneca vaccine comes nowhere close to, in terms of the concentration of neutralizing antibody that's induced following 2 doses of the Pfizer vaccine or the Novavax vaccine. So we're going to expect more breakthrough infections with vaccines that are less immunogenic, induce lower concentrations of antibody responses, but at the same time, our purpose is no longer to try to prevent infections. Our purpose is to protect against severe disease. So that needs to mean that we need to make sure that people get vaccinated, period, to prevent severe disease and to stop believing that we're vaccinating against infection. Protection against mild disease is also important because some of them go on to develop sequelae, long COVID. In this, about 20% of the breakthrough infection did in fact have persistent symptoms for greater than 6 weeks, but that is not the focus of vaccination, especially in the context of a crisis that we're facing. So what do we know about the antibody? Like I said, there's waning of antibody that takes place. So we're not too clear exactly whether this waning of antibody translates into diminished protection, but the most recent data suggests that it does. So what we see here is the antibody concentrations at different time points of 2 weeks after they've received a second dose for the Pfizer vaccine and AstraZeneca vaccine. And as you can see, as I mentioned, the immune responses of the AstraZeneca vaccine to start off with is substantially lower compared with the Pfizer vaccine. And then you get this waning of antibody. By day 70, you got very low concentrations of the AstraZeneca vaccine in the absence of large ongoing circulation of the virus. If there's ongoing circulation of the virus, this sort of kinetics can very much change because that ongoing exposure will boost your antibody responses in all likelihood. So with this sort of decline, waning of antibody, we do expect there to be waning protection. Although we've got these memory B cells, those memory B cells will start producing antibody much more rapidly than in the absence of having those memory B cells, which usually takes them 2 to 3 weeks. But the concentration of antibody at a point in time, if that is what is required to protect against infection, might not be where it should be to be able to prevent the infection, although a robust recruitment of those memory B cells might attenuate the clinical course and reduce the viral load, reduce the duration of shedding of the virus. So what else about so vaccine efficacy at 6 months? This is data from the Pfizer vaccine, and they've been making a strong case to try to convince people to have a 3rd dose of vaccine because of the efficacy trial. These are data from the efficacy trial, and this is against all severity illness. They report a decline of efficacy. This was after 7 days after the second dose, the initial analysis, and where the efficacy was estimated less than 2 months after the second dose, where they reported efficacy in a region of 94%, and that has gone down to 87%. Does this mean that we need a 3rd dose? The short answer is that it does not mean we need a 3rd dose. In fact, that will be a complete waste of vaccine, because what they also report in this data is that there was no change when it comes to protection against severe disease that remained persistently above 90%. And in fact, in Israel, what they've recently shown is that although they've had a decline in effectiveness, mainly due to the Delta variant arising there, the effectiveness of vaccine has dropped from initially reported around about 90% to now to as low as 40% perhaps. So there is a decline, and that possibly is a function of the increased transmissibility of the Delta variant, as well as slightly reduced sensitivity of the Delta variant to the antibody activity that's induced, but also because of waning of antibody. But despite a decline in protection against mild disease, there's no change in severe disease. And then the question comes, if you're going to give a 3rd dose now, so how long is that going to last? And are we in a position as a globe to continue vaccinating people every 6 months, as some would like us to do, not because it's going to be of major public health benefit, but because it's pretty much going to be a money spinner. So we can basically then talk about, try to figure out what is the need for booster doses of vaccine. And this is a modeling exercise. And it tells us that depending where you're starting off in with your efficacy, we can sort of get some idea that we probably might change the frequency that booster doses would, what frequency there might be for booster doses. And this is looking at, so as an example, let me use let's use where you start off with efficacy against of 90%. And this is Pfizer vaccine or the Novavax vaccine or the Moderna vaccine. These are vaccines that have got efficacy against 90%. What we expect is that we would get waning of antibody, and that in fact your protection against mild infection would actually wane over time. And we've already seen this transpire in Israel, as I mentioned. Initially, they reported effectiveness of 90%, and 3-4 months later, that effectiveness had gone to 60%. So if you want to get that back up, yes, you might well require a booster dose to get that protection against mild disease up. But when it comes to severe disease, in Israel, and similar to what's being projected here, even at 6 months later, there's very little decline. And under a worst case scenario, depending on the half-life of the antibody, you basically might require a booster maybe every 2 to 3 years. But certainly not every 2 to 3 months or every 6 months for that matter. But it depends what you're trying to protect against. And even the booster response might be specifically for those category of individuals with some sort of medical condition that keeps them at risk of severe disease. If you start off with a vaccine as an example of efficacy of 70%, that waning of antibody and protection against mild disease is obviously much more rapid, as I discussed earlier. And then you'll need to get even more frequent boosters than you would with a Pfizer vaccine if your vaccine efficacy, or the efficacy of the vaccine to start off with at the start was only 70%. But protection against severe disease, again, I'm not too convinced about this modeling data right now because the evidence is that closer to 6 months later, the efficacy against effectiveness against severe disease has actually remained above or in the region of 90% for most of these vaccines. So lastly, and to go on to a few other issues, vaccination of people that have been previously infected. So this is one of the key questions faced in South Africa, especially when we were vaccinating during the midst of a resurgence. Since many people got infected, they were scheduled to be vaccinated, and they didn't know what to do next. Some of them might already have been vaccinated with the first dose, waiting for a second dose, and unfortunately got infected in that in-between time. What we do know, and this study is now on the Pfizer vaccine with very similar sort of data available for AstraZeneca vaccine. This is for Pfizer or Moderna, but there's similar study data now available for Pfizer on its own as well as for AstraZeneca on its own, is that when a person is infected with a virus, that is a potent priming event. It primes the immune system. And in fact, what you see in red here is that those individuals that were previously infected before they got their first dose of vaccine, they mount a really good immune response, both in IgG antibody responses to the spike protein, to the receptor binding domain, as well as a neutralizing antibody activity. Really good immune response after a single dose of the vaccine, way above after what is observed after a single dose of a vaccine in individuals that were not previously infected with the virus. In fact, in those individuals that were previously infected with the virus, there's very little benefit in them getting a second dose 1 or 2 months after having received the first dose, because the neutralizing antibody activity doesn't actually increase. For those individuals that weren't previously infected, the priming dose basically induces an immune response, but it's boosted. The second dose now really acts as a booster dose, and that shoots up their immune responses. But interestingly, they actually end up at a level where that neutralizing antibody responses, both against D614G, the alpha variant, as well as the D614G variant, as well as the beta variant, the neutralizing antibody responses that's induced by a single dose of vaccine in an individual that's been previously infected with the virus is actually better than a neutralizing antibody response that's induced after 2 doses of the Pfizer or Moderna vaccine in an individual that was not infected with the virus before receiving the first dose. So in South Africa, where right now the estimate is between 50 to 70% of people have been infected already with the virus, knowingly or unknowingly, and this is based on the serious surveys and some other modeling that's been done, 60 to 70% of South Africans have already been infected. We can be resting in a comfort zone that even a single dose of the vaccine, 14 days after that, for probably to 60 to 70% of people that are vaccinated, that will probably already provide high levels of protection against severe disease. which probably could be even higher than exists in another country where very few people, as an example in New Zealand or Australia, where very few people have been infected, them needing to get 2 doses of vaccine, they still won't have antibody responses of the magnitude that a majority of South Africans will have after a single dose of vaccine, because we've been primed. And I'm not advocating that's a good reason to get infected, because that natural priming has come at tremendous cost. The mortality rate from COVID-19 in South Africa is not 75,000, it's not 80,000, it's 220,000 plus. The number of people that have died per million of the population in South Africa right now, based on the South African Medical Research Council, excess mortality is 4,000 per million of the population, amongst the highest in the world. And that is because the virus has continued circulating completely uncontrolled in South Africa, where we've had 70 to 80% of our population now, or at least 70% that have been infected with the virus. But that paradoxically puts us in a good position in terms of how well we'll mount an immune response and how well we can expect these vaccines to work in those people that are vaccinated. For those that are not vaccinated, their neutralizing antibody levels are not here if they've been infected. Their neutralizing antibodies are here. So do not believe that because you've been infected, you've got good immunity. You certainly don't have good immunity in protection against reinfection, and especially not for things such as the Beta or Delta variant. You might have protection against developing severe disease. So again, this is another study addressing the question about the timing. So after a person has had natural infection, which is the best time to receive at least a single dose of vaccine? And these data involve relatively small numbers, so you can't be very conclusive. The confidence intervals are very wide. There doesn't seem to be much difference whether a person receives the vaccine 1 or 2 months, 2 to 3 months, more than 3 months after past infection in terms of the amount of antibody concentration. When it comes to the neutralizing antibody concentration, there's some suggestion that delaying it to 3 months probably might have some advantages, and that shouldn't come as a surprise. And the reason why it shouldn't come as a surprise is we know that SARS-CoV-2 actually affects your immune system. And it actually affects the manner in which your immune system is going to be able to respond to other infections as well as to vaccines. So you need to give your immune system some time to recover before receiving a vaccine after you've had COVID-19. In addition to which, remember that after you've had COVID-19, your antibody responses are going to be reasonably high. You're going to be protected in that immediate future, at least against severe disease from the variant that probably caused your infection in the first place. So give your immune system some time to recover. You already got some comfort that you are protected because you've already recovered from COVID in the immediate past, and you probably will end up with slightly better immune response if you delay that vaccine 2 to 3 months. So like I said, in South Africa, the majority of healthcare workers have had the Johnson & Johnson vaccine as a single dose. The single dose of Johnson & Johnson vaccine recently was reported to provide at least 70% protection against Delta variant with regard to protecting against hospitalization, and 97% in preventing deaths. 70% against hospitalization is a great feat, but we can do better, and more so for healthcare workers. 70% is nowhere close to the 90% that's been reported against hospitalization and death due to the Pfizer, where people are vaccinated with 2 doses of the Pfizer vaccine, 2 doses of the AstraZeneca vaccine for that matter, or many of the other vaccines, where protection against hospitalization is north of 70%, is 90% and above. But in the absence of us not having other options, the use of the Johnson & Johnson vaccine was fully justified and has protected lives. But we can do better for healthcare workers, and the way to do that is to provide them an additional dose of vaccine, and in particular the Pfizer vaccine. And these are data, so there's a number of data points, and most of this has currently mainly involved the AstraZeneca vaccine with the Pfizer vaccine, looking at 2 doses of AstraZeneca, 2 doses of Pfizer, or AstraZeneca followed by Pfizer, and vice versa, Pfizer followed by AstraZeneca. And this is just one of perhaps 5 or 6 studies that have come out in the past month addressing this issue. So in this study, what we see is that individuals that received, now the reason why I say we can extrapolate to Johnson & Johnson, those studies are underway, but at the same time, we know the Johnson & Johnson and AstraZeneca vaccine are almost identical in the immune responses that they induce, both in neutralizing antibody concentration, as well as binding antibody, both against the ancestral virus, as well as against the beta variant. They're almost identical in the immune responses that they actually induce after a single dose of the vaccine. because they're using similar technologies, I think it's safe to be able to extrapolate, and find the results will be out soon for another study, which probably will confirm what I'm saying, is that the type of immune responses we're seeing with AstraZeneca combined with the Pfizer is what we will see for Johnson & Johnson combined with Pfizer. So receiving 2 doses of the Johnson & Johnson vaccine, the AstraZeneca vaccine induces immune responses as we expect, but those immune responses, when looked at a week after the second dose and at day 56, it's much lower than individuals that receive 2 doses of the Pfizer vaccine in green, or a single dose of the AstraZeneca vaccine followed by the Pfizer vaccine, or a single dose of the Pfizer vaccine followed by the AstraZeneca vaccine, which is in blue. But as you can see, starting off with a non-replicating vector-based vaccine, the AstraZeneca vaccine followed by the Pfizer vaccine is better than starting off with a Pfizer vaccine followed by the AstraZeneca vaccine. This is AstraZeneca followed by Pfizer, Pfizer followed by AstraZeneca. In addition to which, what we also see is that the neutralizing antibody responses are better with a combination of AstraZeneca followed by Pfizer compared with Pfizer versus Pfizer, and the same thing would apply. BNT, the Pfizer with AstraZeneca would probably fall somewhere in between this. When looking at T lymphocyte responses at day 56, there is overlap, but the AstraZeneca vaccine followed by Pfizer is the one in red at day 42, as well as the day 56, seems to be slightly better compared to even 2 doses of Pfizer and Pfizer. So I believe strongly that this heterologous approach, even though we don't have efficacy data, but from all that we understand, in terms of immune responses, how immune responses are able to predict protection against mild infection, the role of T lymphocytes, and protection against severe disease, there's good reason to believe that a combination, the heterologous approach, in fact, would probably be better than the homologous approach, including for the Pfizer vaccine. And these are the type of decisions which government and its advisors need to be thinking about, because it influences how efficiently we're able to use the vaccines that we've got currently available to us. So finally, a few words on herd immunity and COVID-19 vaccines. And this is an early study from Israel, which really initially showed great promise that with some vaccines, we might actually be able to get significant amount of interruption of transmission of the virus. And this study was done at a time when mainly the Alpha variant was transmitting. It was done amongst households of healthcare workers where someone has got infected, they went to the household, and they looked at what was the risk of other household members being infected by that index case, as well as whether those other household members were basically vaccinated or not. So first and foremost is to look at what was the risk in different households. And I think the first thing is that children under the age of 12, even if they were unvaccinated, their risk of being infected with a virus when it's introduced in a household was much lower than the risk of adult contacts. What we see there. If the person was vaccinated, their risk of being infected was substantially lower than someone that was unvaccinated. The summary of all of this is that vaccination resulted in about an 80% lower risk of being infected amongst adults as well as teenagers. So vaccination could play a role in interrupting the transmission of the virus. On the other side, just isolation on its own probably worked as well as someone being vaccinated in terms of reducing the risk. But obviously the difference is that these individuals would continue with a normal lifestyle, whereas these individuals needed to be in not isolation, in quarantine for at least 14 days, in isolation for at least 14 days. So summary, at the time of the Alpha variant, some suggestion from Israel showing probably reduced chances of transmitting within our household, especially in people that were vaccinated, when people were vaccinated. This is a study which literally came out yesterday from the United Kingdom, and this I think is more in the context of both Alpha as well as Delta variant circulating. I'm not going to go into detail of this, but what it basically shows us both for the AstraZeneca vaccine as well as the Pfizer vaccine compared to those that were unvaccinated and the risk of there being secondary cases in the households of where introductions took place. Both of these vaccines have got about reduced the risk of household transmission by about 50%. Not 100%, not 90%, not 80%, about 50%, which means that vaccination people that are vaccinated can still transmit the virus onwards to others that are in close contact with, but 50% less likely compared to those people, compared to people that are unvaccinated in terms of their chances of transmitting the virus onto others. For those people that were vaccinated, unfortunately, in the study that had breakthrough events, what they actually showed is that the viral load in those individuals was actually quite high. But again, to emphasize, the chances of them being infected in the first place was significantly lower than individuals that were not vaccinated. So the breakthrough events here would be much, much lower to start off with. And then if there are those that are actually infected, unfortunately for those, their chances of transmitting the virus is probably similar compared to an unvaccinated person. But overall, at a population level, there's about a 50% reduction in terms of household transmission. Now, what does this all mean? So what we saw happen in Israel and the United Kingdom is those two countries are way ahead in the game in terms of ensuring people are vaccinated. In the United Kingdom, I think they're close on to 90% of the population, of the adult population now having been vaccinated. Similarly so in Israel, and that's more than about 2/3 of the overall population. In South Africa, until recently, we're sitting now probably, I think, the last time I checked, probably around about 20% of South Africans now having received at least a single dose, but much of that vaccination has taken place during the course of the current resurgence. Now, what we see in Israel, where much of this vaccination, as well as in the United Kingdom, much of this vaccination had already taken place by June, July. Yet what they observed was a resurgence, largely because of the Delta variant in both Israel as the United Kingdom. The United Kingdom, Israel is still somewhat an upward peak. The United Kingdom is on downward trajectory. So despite this high penetration of vaccine, they still experience a resurgence. And that is what we need to become used to. And that tells us another story, that we're not going to get to herd immunity, even if we vaccinate magically 40 million people or 35 million people, which Department of Health still believes they'll be able to do by the end of the year. We're not going to get to herd immunity, so we should stop using the word herd immunity, because the experience from United Kingdom, from Israel, and many other countries now, Denmark, and many others, shows us that you're still going to experience resurgences. The difference being, as opposed to the past, when you had these resurgences, we had large number of cases. When you look at what's happened with mortality in the United Kingdom, in Israel, as opposed to this resurgence that you're seeing in cases, in infections, the increase in number of deaths in the United Kingdom as well as Israel is a fraction of what it was during the course of the past two waves. And a high percentage of this obviously will be people that are unvaccinated, but amongst them are people that will be vaccinated. But that's also a manner in which how we interpret data. If we were at this point and we said that 80% of people that are hospitalized or dying are vaccinated, that would be much greater concern than when we say 80% of these people that are hospitalized or dying had been vaccinated. The reason being, the magnitude, the number of deaths that are occurring is so nominal now, in addition to which, when 100% of your population is vaccinated and you have breakthrough infections and people die, 100% of people that die will have been vaccinated. That doesn't mean anything that the vaccine is not doing what it's doing. What the vaccine has done is reduce the incidence, the rate per 100,000, per million of the population, of the number of people that are dying. So the experience from the United Kingdom and Israel, and in the United Kingdom, as all of you know, the football stadiums are full. Arsenal are performing as poorly as they've performed even before COVID-19, unfortunately for me. The football stadiums are full, but the bottom line is that they've now come to accept that the virus is not going away, herd immunity is not going to materialize, but they're protecting people against severe disease and death, which is what matters most. And what we need to do, as they've done in the United Kingdom, is we need to get to the point where South Africans are vaccinated to a similar level, and we simply can get on living, get rid of the mask, get children back into schools, get the normal lifestyle. The only way we can do that, the only sustainable manner in which we can do that, is to ensure that at least 85 to 90% of South Africans above the age of 35 and above the age of 60, and especially people with underlying medical conditions between 35 and 50 and 60, receive their vaccines immediately. If we can do that, we can be back to a relatively normal lifestyle before the December holidays, and the teenagers can go out partying to their age parties at the end of the year. Like I said, Delta variant, a major problem across the world, and then we've got Gamma, and then we've got Lambda on the horizon. But across all of this, what we need to accept is that the virus is going to continue mutating. Fortunately, the mutations that have taken place up to now might compromise the ability of the virus to protect against mild infection, but certainly has not done so when it comes to how well these vaccines work, phenomenally well, in protecting against severe disease and death. And this is a picture for South Africa. Largely now we're sitting with majority of cases being due to the Delta variant. There is a new variant that's on the horizon, unfortunately, being identified in South Africa, which is also of concern. Well, currently of concern to me, not designated as a variant of concern. And this is a variant which is sort of chimeric between Beta and Delta, which might well create unfortunate problems. But again, I don't think that would be an issue when it comes to protecting against severe disease. It would might be an issue in terms of infections, mild infections. So last but not least, sorry, I skipped that slide. So this is really just to reflect on what I just said. So we might have a new variant that evolves. And past infection previously, in fact, what the ancestry virus showed in this longitudinal study, that past infection didn't protect too well against reinfection due to the Beta variant. In fact, there was very little difference at the initial stage of observation, and after that, about a 25% lower chance that people that had past infection without any vaccine, that they actually were protected against infection due to the Beta variant because of the mutations that have taken place. And this is over and above a further reduction in protection from past infection because of waning of antibody. And we can expect this sort of scenario to continue playing out if the virus continues mutating, evade the type of immune responses that are induced by one variant, especially against the antibody that's induced against the spike protein. Then we can experience other variants evolve, and it's unpredictable as to how well those past infections would protect against reinfection, but not necessarily prevent protection against severe disease. So last slide is really to talk to you about a little more about herd immunity. By now, hopefully I've convinced you that the vaccines that we've got are not vaccines that are going to be useful to get us to herd immunity. The protection against infection vary between vaccines depending on how immunogenic those vaccines are neutralizing antibody responses. The protection changes over time because of waning of immunity of the neutralizing antibody. The protection changes over time when there's evolution of a new variant. And all of these vaccines, none of them have been able to show sustained protection against infection and mild disease, not against severe disease. To get to herd immunity, we need to be able to protect against infection, mild disease. We need to make sure that people shed the virus for a short period of time as possible. With Delta variant, like I said, we probably need to get about 85% of people to have that type of protection. None of the vaccines currently provide 85% protection against that type of illness due to the Delta variant. In addition to which, that doesn't mean 85% of people need to be vaccinated. It means 85% of people need to have that type of protection, which will probably translate into 100% of people needing to be vaccinated, because some people, unfortunately, don't have the type of response that we require. So herd immunity was an aspirational goal. I myself, once upon a time, wished for it, perhaps last year this time. But after the South African data came out in January on the AstraZeneca vaccine, I mentioned then, and I reiterate now, I need a recalibration of what COVID vaccines are all about. It's about saving lives. It's about preventing hospitalization. The vaccines do an excellent job when it comes to that. COVID vaccines are not about herd immunity, not this generation. It might be a future generation of coronavirus vaccines, which span across protecting against infection due to any coronavirus. But those vaccines are not the tools that we've currently got available to us. So unfortunately, herd immunity is not what we need to base our future responses to, our targets when it comes to vaccines. Our targets need to be about ensuring we get adequate penetration of vaccines into the arms of those individuals at highest risk of developing severe disease, which means that we can go through another resurgence come November, December in the holidays, but we can prevent having further lockdowns because our healthcare facilities won't be under pressure, people won't be dying in large numbers, and there should be zero reason in that instance for government to have restrictions, because they need to allow for ongoing transmission of the virus, because that is a reality under which we need to come to live. And that speaks to my first conclusion here. We need to recalibrate our expectations of the pandemic, how we respond to it, the expectations of the first generation of COVID-19 vaccines in the midst of a virus which has shown much greater propensity to be able to mutate than what we had predicted perhaps a year ago. As I mentioned, all of these vaccines are going to work extremely well against severe disease, but they're variable when it comes to how well they protect against mild disease. But against all of this, the protection against severe disease for the majority of these vaccines, especially after 2 doses, is above 90% for hospitalization. I do believe for the Johnson & Johnson vaccine, and I'll go out on a limb here, that individuals that receive the Johnson & Johnson vaccine should get a dose of the Pfizer vaccine to optimize the protection. And there's a number of reasons which time doesn't permit as to why healthcare workers in particular need to get an additional dose of Pfizer vaccine, because their protection, even if it's only increasing from 0 to 50% against infection, is important in terms of the risk they pose to others for onward transmission in healthcare facilities. The single dose of the Pfizer vaccine, as I showed you, neutralizes really robust antibody responses in individuals that were previously infected. It's important in South Africa, where a high percentage of the population have already been infected. And then this whole issue of the heterologous approach, again, speaks to the Johnson & Johnson vaccine, the need to offer as a Pfizer vaccine in South Africa to healthcare workers. And in fact, in the South African program, if it was my choice, I wouldn't be using Johnson & Johnson as a single dose and Pfizer as 2 doses. For the entire population right now, I would be recommending a starter for the Johnson & Johnson and have a boost with Pfizer for the entire population. And yes, that is not authorized for use. It's not licensed for use. It's not authorized for use. But South Africa in the past has basically adopted schedules of vaccine, including in children, which were not licensed, but based on the recommendations of experts in the field in the National Advisory Group of Immunization, who are the group that should have been advising government, which was actually established by government, which WHO indicates should be tasked with a mandate of advising government. And this is a group that has been in existence in South Africa over 25 years, which government decided not to actually engage with, but rather set up a parallel project where they basically made mistakes, a number of mistakes that has come at the cost of lives of people. So lastly, again, herd immunity is not an option. We need to stop thinking about it. Politicians need to be de-educated about using the term herd immunity and community immunity. That's not the reason we wanting to vaccinate 35 million people. The reason we're wanting to vaccinate 35 million people is to include as many people that are at risk of hospitalization and death so that we can prevent hospitalization and death through vaccines. Vaccinating 35 million, if the majority of them are people between the age of 18 and 35, is not going to put us in any more favorable position when we experience another resurgence towards the end of the year. Because if those people that truly require a vaccine, that at highest risk of developing severe disease and dying of COVID are not vaccinated in large numbers, then we're still going to get large numbers of people, unfortunately, end up in our hospitals. So thank you for your attention, and hopefully you found this talk useful, and look forward to any discussions.